Welcome to Math1081 Discrete Mathematics at UNSW Sydney. Possibly I should say welcome back, because you may have already been looking at lecture notes for sections 1 and 2 of the course. This is section 3, in which we'll be talking about proof and logic. Now, many of you may well have done some proofs in other subjects, earlier at university or perhaps at school, and you will probably have realized that proof is really a very essential part of modern mathematics. In fact, if something is not actually proved, we would, in some senses, hardly regard it as mathematics at all. I'd like to give you a bit of background, just to let you know that this has not always been the case. If you go back to ancient times, say Egypt, Babylon, basically mathematics there was a collection of rules. They appeared to work, they appeared to give the right answer for the problems that were being asked, and it doesn't seem that they wanted anything more than that. In case that gives you a very underwhelming view of Egyptian and Babylonian maths, I'd like to just mention a couple of things that they did. What were the Egyptians interested in? Well, of course, we all know one thing they were interested in, which was pyramids. Supposing you're engaged in constructing a pyramid, and you wish to know how much rock you're going to need to build it up to a certain point. So let's say you've got a certain height h that you're aiming at. You know the side length of the base, let's call it A. You know the side length at the top, let's call it B. That's not the entire top of the pyramid, of course, but the top of this section we're looking at. By the way, they would not have called them H, A, and B because they didn't have algebra. They would have said something in words. Question is then, from that information, can you find the volume of this partial pyramid? Well, yes, you can. I'm not going to show you how. It's not a terribly difficult exercise, and I think you should be able to do it, but it might be a little bit harder than you think. Please have a try at it. And if you can do that, you might be reasonably impressed with ancient Egyptian mathematics. It's not as primitive as you might perhaps imagine. Here's another example. The Egyptians used to do arithmetic with fractions. Let's say 47 over 79 by way of example. Now, if they were working with fractions, a peculiarity of Egyptian mathematics is that they did not want to use fractions with any numerator other than 1. They would not have had a 47 up there, they would only have had 1. That means that to deal with 47 over 79, or, to put it in a practical way, if you have 47 objects and you wish to divide them equally among 79 people, then they would have to write this as a sum of what we now call unit fractions. In other words, fractions where the numerator is only allowed to be 1. Now, of course, on the face of it, there's a very easy way to do that. You can just say 1 on 79 plus 1 on 79, etc. Unfortunately, there's a complication, and I'm not sure whether anybody understands why the Egyptians introduced this complication, but they didn't want to use the same fraction more than once. So 1 on 79 plus 1 on 79, etc. is not allowable. You might like to try this one. Can you write 47 over 79 as a sum of fractions where all of the fractions have numerator 1 and all of them are different? I think you'll find that's actually quite a hard problem. The Egyptians could do it. And again, as I said before, I'm mentioning this so that in case you have a rather low opinion of ancient Egyptian mathematics, I'd like to suggest it's not justified. They could do some things which even nowadays people might find quite difficult. Babylon, here's an example from Babylon. One of the things that they were interested in was right-angled triangles where the side lengths are all integers. Now, I'm quite sure you know an example of that, a 3, 4, 5 triangle. And we know that that is a right-angled triangle because we have 3 squared plus 4 squared equals 5 squared. I expect you know other examples of this. We can say 5 squared plus 12 squared equals 13 squared. And there's some more. There's many more, actually. Here's one you possibly don't know. 4,961 squared plus 6,480 squared equals 8,161 squared. Easy to check, of course. Once I tell you that, easy to stick the left-hand side into a calculator, stick the right-hand side into a calculator, and check that the two sides are equal. But how would you get that if I didn't tell you? That's a lot harder. The Babylonians could do that. Their records are preserved. You may have heard how they kept records. They would have a slab of mud. They would make markings on it, symbolic markings, with a sharp stick. They'd then bake the mud in an oven to make it harder. And that worked so well that some of those tablets are still preserved and still legible today. And there's one of them which has these numbers on it. It seems quite clear that they knew this equation. Not that they would have written it as an equation, but it seems clear that they knew it. It seems, to me anyway, impossible that they should have done that by trial and error. 3, 4, 5, yes, maybe. Probably. 5, 12, 13, maybe. This last one, could they have got that by trial and error? Well, frankly, I just don't believe it. So the mathematics that they had available must have been rather more sophisticated than they've left records of. So, ancient mathematics, not as primitive as you might think. It had lots of problems that they could solve, lots of techniques, lots of calculations they could do. What they didn't have was proof. That came along with the ancient Greeks. The Greeks decided they were not happy with having methods that just appeared to work. Even if it had worked many times without a failure, that was not enough for them. They wanted to prove that their results were true. And that's the culture that's lasted through to modern mathematics. We want to prove that the results we claim are true. And there's a couple of reasons for that. First of all, we'd like to be quite sure as we possibly can be, that what we're saying is true, that it's not just a coincidence, that it's always worked and will always work in the future. But it's more than that, because we don't just seek knowledge, we seek understanding. We want to understand why the techniques work, why the facts that we state are actually true. We want to know how they're related to each other and how they fit into the big picture. So, here are some concepts of the word proof that you'll meet with nowadays. Of course, the one that we're talking about in this course is mathematical proof. And we do it, as I've already hinted, in the ways that the ancient Greeks did it, the way the ancient Greeks taught us. And that's the following, that you take certain facts as a basis for your subject. Now, you can regard them as things which are undoubtedly true and don't need any further argument. You can, if you want, regard them as just being the rules of the game. And you want to play a different game, then you can change the rules. But whichever way, you have certain facts. The Greeks referred to them as axioms, and we still use that word today. And on the basis of those axioms, you deduce further facts. The point is that if you accept the axioms as true, and if your logic is correct, then your results must be true as well. There is no possibility of anything going wrong with that, with the exception, of course, that proofs are done by humans, and humans do make mistakes. Apart from the possibility of human error, the results you get from true axioms by using accurate logic are certain. Just to give you a couple of ideas of the sort of axioms that the Greeks used, here are the sort of things that you see at the beginning of Euclid's work on geometry. The first assumption he makes is that if you have any 2 points, then it's possible to draw a straight line between those 2 points. Now, I don't know about you, you might not agree, but for me, that seems quite clear and obvious, quite acceptably true. That is not something that I'm going to lie awake at night in bed worrying about whether it's actually true or not. That seems a perfectly acceptable basis for starting off geometry. Here is Euclid's second axiom. Again, it begins with 2 points. And in this case, his claim is that given any 2 points, you can draw a circle where one of those points is the center and the other one is on the circumference. Again, something which, to me at least, seems quite clear, and I don't have any problem with accepting that as a basis for geometry. There are further axioms. You might know that one of them is regarded as somewhat more controversial and not definitely true. That's called the parallel postulate. You might like to look that up and find out some things about it. But by and large, we have axioms which are quite acceptable, and insofar as they're true, even the parallel postulate, if you're prepared to accept that it's true, then the conclusions that you get must also be true. Here's some more proof that you see nowadays, scientific proof. Now that's achieved by induction. What that means is that you do an experiment or do an observation, you do it, let's say, 1,000 times, and if it works out the same way every time, then you say, well, okay, I believe that's always going to happen. It's going to be true the 1,001st time, the 1,002nd time, and so on forever. Now, that in principle can't be certain, because perhaps the first 1,000 observations you made were in some way special. Perhaps the first 1,000 experiments you did were set up badly, and perhaps under different circumstances things might happen differently. You cannot be certain about scientific proof. On the other hand, there are certain scientific theories which have so much confirmation that basically you can regard them as certain. Gravity is an example. Supposing I hold a pen up here right near the camera, and if I drop it, what's going to happen? Well, of course you know what's going to happen. It's going to hit the table. You're not going to expect that it flies up and hits the ceiling. In fact, it's even better than that, because if it did fly up and hit the ceiling, you very likely wouldn't believe it. You would say it was a trick. So gravity is so well confirmed and so thoroughly believed that you're prepared to accept it even against the evidence of your own eyes. Still, scientific proof is not as certain as mathematical proof. Here's something else that's very important. Statistical inference. Now, this is the kind of thing that you see in the media, for example, when there's an election coming up. And they will say, we've taken a survey, we asked so many people who they're going to vote for, and on the basis of these results, we believe that the XYZ party is going to win the next election. If you look at some of the more reputable surveys, they'll even give you a bit more information than that. They might say, we believe that the XYZ party is going to win the election, and we're 95% sure that we're correct. So that's what's happening here. On the basis of certain observations, it's declared that some conclusion is likely, and we can also give an estimate of how likely that is. Once again, that clearly is not certain. It's not guaranteed. I'm sure you've all seen examples where the polls have predicted one thing and the outcome has been different. So you can't be certain of the result from a statistical inference. After all, if you're saying that you're 95% certain that you're correct, then you're admitting there's a 5% chance of being wrong. These things, of course, are all very important in the face of things which cannot be predicted with certainty, but they're not the same as mathematical proof. I'll just mention one more item, which you might know about if you watch some of the popular TV CSI shows and things like that. Legal proof, according to the catchphrase, is supposed to be beyond reasonable doubt. Well, if that's how legal proof is, then you might regard mathematical proof as being beyond any conceivable doubt at all. Before we get into the course, just a few suggestions as to how you should study proofs. Well, the sad thing is, the bad news is, there aren't any shortcuts. You have to practice. We're going to look at many useful techniques. There aren't any foolproof recipes. There's no step-by-step procedure by which you can do proofs. There's nothing which says, step 1 I'll do this, step 2 I'll do that, step 3 I'll do that, and there's the proof. Simply cannot be done. It's not like, for example, to take some things you're very familiar with, it's not like the quadratic formula. If you know the quadratic formula, which I'm sure you all do, then you can solve any quadratic you like. Just plug in different numbers. Furthermore, the way you solve the next quadratic is going to be, apart from the different numbers, exactly the same way as you solved the previous quadratic. It works every time, and more than that, it works the same way every time. If you'd like to think of another one, which you may have learned more recently, perhaps, for example, in section 2 of the discrete maths course, that would be, for example, using the Euclidean algorithm to find the greatest common divisor of two numbers. So say 79 is, say, 1 times 47 plus 32. 47 is 1 times 32 plus 15, and I'll leave you to finish that off for yourselves. If you've studied this, in Math 1081 or elsewhere, you will know it's just like I said for the quadratic formula, which is that it'll work every time. And not only that, but it'll work the same way every time, other than substituting different numbers. Proofs, you must understand, are not like that at all. There's no step-by-step procedure for doing proofs, and if you're wanting to find one, you're going to be wasting a lot of time on looking for something which doesn't exist. So that's very important to get yourself into the right mindset straight away. You can learn useful techniques, but you can't learn a step-by-step procedure because there isn't one. What are we doing in lectures in that case? Well, what I'll do is I'll look at lots of examples of proofs, and I'll usually do it in the following way. I'll show you the result that we're intending to prove. I'll ask you to pause the video for a little bit and see if you can write down something, any ideas, anything that's relevant, any logical structures. We'll learn these things as we go through the course. Try and write down some things which are relevant. Perhaps you can even manage to prove the result all by yourself. Once you come back to the video, I'll do a bit of discussion on the problem, some ideas that we might use to solve it. I'll give you a complete solution, and we'll then try and learn some lessons from that particular solution. Lessons that we can hopefully apply to future proofs. There are some books that we use for this course, if you're taking it on site at university, which I can certainly recommend, and I'll leave you to look those up further. Franklin and Dowd is the official textbook for this course. The book by George Paulier, How to Solve It, is one of my personal favourites, and I do recommend trying to find that. One other important thing which is connected to what I've just been saying, that the results that we're proving are generally quite unimportant, because what we're studying in this section is methods of proof, methods of investigation, methods of proof. And the actual results that we look at are illustrations of those methods. What it comes down to is that whatever proofs we do in this section, you really can't expect that proofs you see in tests and exams will be like that. They'll use similar ideas, but the actual subject matter, the actual topics, could be very, very different. I think that's enough by way of introduction. Let's start looking at some problems.